So, we're talking about strain and compatibility. That's sort of the topic of the chapter, let's say. And we talked about strain, we talked about displacement components, and we solved an example. We talked about rotation. So now we're going to talk about the second important concept of this, let's say, chapter, and it's compatibility. So compatibility is something, actually, you'll see it's quite practical. It's something that will, in a sense, ensure that our efforts will not go wasted at some point when we're trying to solve a problem. And using the idea of compatibility, we will be able to build a solution approach that is alternative to the classical approach. The classical approach says, OK, I'm trying to solve a problem, and I assume that this will be the displacement field. And using that displacement field, I try to calculate the strain. Using the strain, I calculate the stress, and the stress must satisfy equilibrium, etc. And then I try to find the correct displacement field. The alternative approach is, here is the stress field I assume, and such that, let's say, from the outset, it satisfies equilibrium. What is the corresponding displacement field is sort of a reverse approach. And we're going to talk about those two approaches. So compatibility plays a very important role in both of these approaches. So to motivate that, let me first solve a small exercise on the gradient. Okay, so I will, just to remind you, right? So I will say, well, suppose let us pick a function of position, a scalar function, phi, and it's simply x1, x2, x3. And I'd like to calculate a vector such that it is the gradient of this function. And we know that eventually the components, just let me remind you, vi is phi comma I, and therefore, when I put the vector into an array, right? So it's going to be x2, x3, and then the second one is x1, x3, and the last one is x1, x2. Okay. So given a function to calculate the gradient, it is, let's say, rather easy. Okay. Sure, it can be a little bit tedious, but in the end, it is more or less straightforward. So now I am going to reverse this problem. And essentially, I would like to first start off with a vector field. Okay? And I propose a vector field. So it's going to be very similar to that one. Let's say x2, x3. x1, x3. And the last one, I will modify a little bit. I will say, let's say it's equal to x1. So now from the outset here, I'm giving you a vector field. And the question is, find a function phi such that v is its gradient. Okay. So what do? I should take an integral. Right. So how do I start? Component by component. All right. So let's see. So I like to start, for instance, with v1. Now, as I start, of course, we are now believing that there is a phi such that v is its gradient, right? That's the assumption. And so now I'm trying to calculate phi. So if there is such a phi, then v1 is phi comma 1. And that is equal to x2, x3. So now what I can do is I can say phi is the integral of x2, x3, and then I do a dx1, right? Because the partial derivative was with respect to 1. And I can say that phi must be equal to x1, x2, x3. Yes? plus a constant. What kind of a constant? A constant or? Just a constant, okay? Suppose here I had x2. Is that possible? x2. How about x2, x3? How about any function of x2 and x3? Right, because I'm taking a derivative with respect to 1. So let's call that f of x2, x3. Okay, so that's a good start. Let's go to v2. It's phi comma 2. So that's x1, x3. So phi must also be equal to, right? Because all components of v come from the same phi. So phi is also equal to x1, x3 dx2. So that's equal to x1, x2, x3 plus now some other function of x1 and x3. Now let's pause here for a second immediately and analyze what we have so far. Okay, so phi must be equal to this, but also equal to that. So now I compare these two terms and I want to make an analysis. This is my first analysis. I'll make another one. Can I at this point make a simplification? Which is what? Right, so f cannot depend on x2 and g cannot depend on x1, because if this does depend on x2, then there is no way I can match this with that, right? Because these are already equal, and so the remaining ones also need to be equal. So I can delete that and that. So they're gone. So f is at most a function of x3, and g is at most a function of x3. And in fact, we see that they must be the same function, right? So f actually is equal to g. OK, but anyway, even if that were true, let's move on and look at the last one. The last one is x1. So phi must be equal to x1 dx3. And therefore, phi must be equal to x1 x3 plus some function, let's call h of so now I compare all of this. And that's my second analysis. And what's the conclusion? Right. The conclusion is that there is no phi from which I can calculate v as its gradient, because there is no way I can match these expressions such that for all of them they are the same, right? So even from the presence of x1 and x3 here, just these two terms violate everything, because x1 cannot appear in these functions. Okay. So right. So that is the conclusion, that it's impossible to find such a function. Okay. There is no such phi. So the message here is essentially that if I give you phi and you would like to calculate its gradient, that's rather easy, right? But if you want to start with a v and you assume that there exists a phi, then you have to integrate. That already requires some effort, but also you need to ensure that there exists such a phi to begin with, which makes it somewhat, let's say, tricky. Okay? So now the question is, eventually you will see, so I will start complicating this step by step. So it takes some effort, right? This is so easy, whereas this requires some effort, it requires some observation, etc. So before we start putting this effort, is there a way with which we can first check easily whether there is such a phi? And if there is such a phi, if my argument tells me that, okay, there is such a phi, then I carry on with the effort so I don't waste my effort. Okay? So the question is, how can we make sure that there is, right, there is such a phi to begin with? Okay. So now at this point, you might have already forgot some of the, in fact, one of the results that we obtained in the very, very first lecture. And so let me remind you. Suppose I take a function, phi, and then I calculate its gradient. That could be anything. Okay. Then, however, I take its curl. Okay. The result is equal to 0. Okay. So the curl of a gradient is necessarily 0. Okay. So then, now my argument is the following. If phi exists such that v is equal to gradient of phi, right? So if v comes from the gradient of some function, then, right? So it's an if-then statement. Then right? The curl of v must vanish, right? Because v is gradient of phi and curl of gradient is equal to 0. Now I'm going to believe, and this is true with except very small details or technicalities. Now I'm going to say that if I take a vector field and its curl is equal to 0, then v must be the gradient of some function. Okay? So in other words, before I went into this trouble, I could have simply taken the curl of v, and if it is not equal to 0, I would not have gone into the trouble because I know that there is no such phi. And if it is equal to 0, then I would carry on with the integration and go through all the effort. So whenever v satisfies this equation, we say that v, let's write this with a different color. So v is compatible with the, let's say, existence of phi. I'd like to calculate phi using v, and I need to make sure that such a phi exists. I check this condition. If it holds, I know that v does come from the gradient of phi. In other words, v is compatible with the existence of such a function. So indeed, so now let's go back and let us check the components of the curl of v that we already had. So I'm going to, right, so this is v. I'm going to remind you what the components of the curl are. Okay, that's how the curl is given. Okay. Right, so I have the vector field. You can go ahead and calculate this yourself. 3, 2, x1, 2 is 0, minus 2, 3, minus x1. So already the first component is not equal to 0. And now 1, 3, x2, 3, 1, 1. And then 2, 1, x3, 1, 2, x3. So the last one is 0, but the other two are not. Okay. So that is not equal to 0. So since it's not equal to 0, I wouldn't even start with attempting to find such a phi. Okay, so now that's nice, but this is just a motivation. Let's now move towards what we want to employ or what we eventually want to construct, and that will be the displacement field. So now, similarly, I'm going to follow sort of the same argument because it's slightly more complicated. If I have to begin with the displacement vector, right? So its gradient is now going to be or its components form a matrix, and that's our displacement gradient, and that's easy. Okay. So there is nothing very complicated about that. So now, however, suppose I give you a h, and h is a function of displacement field. H is a function of position, and I'd like to construct u out of it. So first, I must ensure that there exists such a u by a similar argument, right? So given h, so we would like to integrate towards, right, u. We must first ensure that there exists such a u to begin with. And now I'm not going to directly give an example here because the argument is what matters. So I'm going to directly skip to the argument. Okay? I'm going to write the counterpart of that. So we remember that if I take a vector, in this case the displacement vector, and then I calculate its gradient, which in this case would be the displacement gradient h, and then I take its curl, then the result, first of all, this is a matrix. Curl is another matrix, but that matrix is zero matrix. Okay. So, again, if, right, u exists such that h is equal to gradient of u, then, right, curl of h equals 0 must hold. And so in this case, we say that h is compatible with the existence of u. Okay? So now, suppose somebody gives you an h. So to calculate u, you first require that h satisfies 0 curl. Okay, curl of h should be equal to 0. So that's a requirement, but curl of h has an expression, right, that we expressed a long time ago. So I will here remind you the, let me say, the implication of that expression. So this is equivalent to saying, right, it's going to somehow involve derivatives, right, here. So the curl of a vector involves derivatives of the vector components with respect to the positions. So here I'm going to also have a similar expression. So you can refer to the very first lecture, and essentially this equals 0 is equivalent to requiring that the components of h and their derivatives satisfy this expression. Okay. So in other words, if h satisfies this expression, then it is compatible and therefore a u exists. And this must hold for every choice of the indices. So mij, it could be 1, 2, or 3, and eventually for any possible choice, this has to vanish. Okay? Now notice that some of the choices are trivial. So for instance, suppose I pick 3, 1, 1. Okay? So 3, 1, 1, 3, 1, 1. It's automatically satisfied. Right? Some of them are trivial, but some of them are not trivial. So let me say 3, 2, 1. In that case, 3, 1, 2. And then here, 3, 2, 1. Right? this is not a trivial expression. There is no reason why the derivative of component 3,1 with respect to 2 should be equal to derivative of 3,2 with respect to 1. Absolutely no reason. But it has to be 0 if I would like h to be associated with the gradient of u. Okay, so that's why it is a requirement. Okay, so now, but let us check, and we could have done the same thing before for the previous example. I didn't, but let me just check to make sure that this is a reasonable requirement. Okay, so I told you that this is equivalent to that, but let me show you that it is indeed so. So indeed, let's say, if, right, hij is ui comma j, so that's the definition of displacement gradients, then, so I'm going to plug hij, so the expression for h in there. So this is hmj, so it would be umj, right? Correct? It's just another index, doesn't matter. So um comma ji is equal to or minus hmi. So umi, u comma comma I, j. Right? And that's 0. Okay, because it doesn't matter in which order I take a derivative. Mathematically, I'm assuming there is some smoothness to the displacement field, so I can easily switch these things, the order of the derivatives, and so the result is equal to 0. So in other words, if h does come from the gradient of a displacement field, then this expression is identically satisfied. You don't have to, of course, have to worry about it. Why do I know that? Well, because to begin with, the argument relies on the fact that if the matrix is the gradient of something, then the curl is, of course, something is equal to 0. And that's what I have double verified, let me say, here. All right? But otherwise, it's something I have to check. Now, let me give you an example. And it's a 2D example. Okay. Just to simplify our calculations a little bit at this point. So suppose we are interested so we're going to look at a lot of 2D cases. So I'm going to call it at this point an intrinsically 2D case. Now, the world, of course, is 3D. So when I talk about an intrinsically 2D case, it means for analysis purposes, considering 2D is sufficient. So such cases are, you might remember from 231 and 232, they are plane stress or strain cases. Okay, so when you have plane stress or strain, you don't have to worry about one of the indices, so you can only worry about the remaining two. So in that case, okay, essentially you go to this requirement, okay, and within this requirement, you now have to change these indices only from 1 to 2. Okay? Again, some of them are trivial. If all of them are 1, there is nothing surprising. Okay? But if some of them do not match, then you do get some results. So the only ones that survive are the following. So this you can check yourself. So you need to satisfy that these two expressions are equal to 0, and then h does come from the gradient of a displacement field. So that's all. Just go ahead, go into that expression as a home exercise, plug in combinations of 1 and 2 for mij, and you will see that these are the only two unique expressions you get. Okay? So anything else you get is, let's say, these two things, they have switched order, but essentially it's the same equation. Okay? So now using this, it's now powerful because I can immediately check if H does come from the displacement of a vector field. And H might look relatively complicated. Okay, so just one example here. So let's say that's H, right? And you have the two requirements. And the first one says that this must be satisfied. So you go ahead and simply take derivatives and check. So the first one with respect to 2, 2x2, and then minus 1, 2 with respect to 1, 2x2, and that's equal to 0. So the first requirement checks. And then you go to the second requirement, right? 2, 2, comma 1. So that's a 1 minus 2, 1, comma 2. That's another one. That also checks. Okay. So now without going through all the trial integrations, you immediately see, or you immediately believe, let's say, that there is such a U, and then you would go on with the effort of finding it. Now, at this point, we're not going to do that, but let me just tell you the vector field is right? 1, comma 1. So with respect to 1, it's x2 squared. With respect to 2, 2x2, x1, etc. So it works. Now, but remember, eventually, that when I integrate something towards the solution, in this case, it didn't work out, but in principle, or let's say in practice, as I do this integration, I will always have some integration constants, okay? So that constant is a function of x3 in this case, but it could really be a constant. So in this case, if you integrate, there will indeed be some constants, and these are d1 and d2, okay? I don't know what their values are, but they are scalar constants. Now, what do they represent? So I'm looking for a displacement field such that h is its gradient. And this is the displacement field, but there are some constants. Yes. Maybe a little bit more technical terminology. Something actually we covered. Huh? It might have to do with the boundary, actually. That's what I was going to comment on in a second. Sort of a condition. OK, so I have my eraser, and I torque it. It has a certain displacement field. Okay? And it has a certain displacement gradient field. And now I do this. I just moved it up. What happens to the displacement gradient field? The displacement gradient field, does it change? The displacement moves up. So in other words, d2 increases, displacement moves up, but these are constants. When I take its gradient, the constants will not appear in the displacement gradient matrix. Okay, so it represents rigid body translation in this case. And I don't know, I don't have any condition, I don't have any boundary condition that tells me what those values possibly are. But if I did, then I would be able to eliminate them. So these are related to, in this case, rigid body translation. And indeed, remember last time I commented that explicitly H is insensitive to rigid body translation. So we see that in here. I integrate H, and I get some arbitrary constants. And eventually, will be eliminated. So these constants will be eliminated, let's say, or their values will be found by additional conditions. For instance, your problem might require that. So for instance, at a certain point, x1, x2 equals, let's say, 1, 1. Okay. Somebody tells you that at that point, my problem requires that u is equal to 0. Okay? So this is the displacement gradient field, and this is the solution, let's say, u. But my problem requires that x1, x2, u is equal to 0. Okay? So you plug in x1, x2 equals 1 in there and set u equals 0. And for that to be true, d1 has to be equal to minus 1, and d2 has to be equal to minus 2. Okay? So you do need, eventually, we will need always some additional conditions. Okay, how are we doing so far? The message, I hope, is clear, right? So to make our efforts worthwhile and eventually to build a solution approach that is based on, that is sometimes more effective, let's say, we will need compatibility, all right? We need to make sure that the matrices we deal with, right, in this case, let's say the displacement gradient matrix is compatible with the existence of a U, because if not, then it doesn't make sense to work with it. All right, so let me erase this part. Now, I started with a scalar example, and then I moved up to something that is almost what we need, the displacement gradient, but not quite. We don't work with the displacement gradient field, we work with the strain field. Okay? So now I need to go to the strain, and there waits for us a very similar argument, but with a grain of disappointment, because the argument that we had so far does not directly apply. Okay? So let's go to strain. So I'll say here that all this is good. We understand what's going on, but we work with epsilon. And let me tell you now what the problem is. So now, by a similar argument, right, because curl of h is equal to 0, let me first try to calculate curl of epsilon, see what that gives us. So that's curl of 1/2 h transpose, okay? And so that's equal to 1/2 curl of h plus curl of h transpose. Now, eventually, I would like to propose let's say, a strain field, but I know that the strain field must be associated with the displacement, and it's associated with the displacement through its gradient, but not directly through the gradient, also through its transpose. Okay? So the epsilon that I have must be somehow compatible with the existence of a displacement field. So first, I check its curl, see what that gives me. Okay? So eventually, perhaps my question is this perhaps equal to 0? It may or may not be equal to 0. And to make that argument, let me call this, just for a second, I'm rarely going to need that notation, but just for the time being, let me call it G. Okay? H transpose, I call G, so that the transpose does not confuse us. So I have the curl of one matrix, the curl of another matrix. Okay? So G, by the way, right? It has components G, Mj, let's say, equal to del U J X M. Because H Mj would have um comma j, and G is its transpose, and to get the transpose, you just switch the two indices, and that's what I've done. I've switched the indices. Okay? So that's the difference between G and H. All right. So now, let's go back and assume that H is the gradient of U. Okay? So then, curl of H is equal to 0. And I don't really need to worry about that. But for curl of H transpose, which I now called G, equals 0, we need. Okay? Okay, so I have to remind you at this point the expression we had. If the curl of H is supposed to be equal to 0, this is equivalent to this requirement. So to check this requirement, I take the components of the matrix and plug it in there. And then I can also explicitly check if that really makes sense. So in other words, H is equal to the gradient of U. I can plug in the expression for H explicitly there, and I get this equals that, so it's automatically 0. Now I'm going to do the same thing again using G. G is H transpose. So I'm going to, this is the matrix, so I'm going to put here G, okay? That's all I'm going to do. So we need, using our previous result, this. So if the curl of G is supposed to be equal to 0, then that's equivalent to the requirement that this expression is satisfied. Okay? Now, why am I doing that? Because if the curl of G is also equal to 0, then in order to check the compatibility of the strain, I can simply require that its curl vanishes, right? Because the first part is automatically 0. If this is also 0, then the curl of epsilon is equal to 0 whenever epsilon is compatible with U. That's the idea, right? But now I want to show you that it's not the case. So if this is supposed to be, suppose this is the requirement, and suppose it's true, but first let me check if it makes sense. I know what G means. G is uj, n, and I go ahead and plug that G in there, right? So this is equal to U j, comma, m, I. On the other hand, this is equal to U I, comma, m, j. I just plugged in the expression for G. Again, remember, I'm doing exactly the same thing I did for H. Okay? But for H, sorry, I have to do this again. In the case of H, when I did that check, it's like a sanity check to just make sure that what I'm doing is meaningful, I got identically 0. It's straightforward. But here, that's not the case. I got uj, comma, mi, and here you have ui, comma, mj. There is no reason why, for instance, if this is 3, 2, 1, and then this would be 1, 2, 3. There is no reason why this should hold. In other words, now this has become not only a requirement, it's an impossibility, because even when I put in the actual displacement field, it's not satisfied, right? So it should have been satisfied if this was a meaningful condition. So the conclusion is that I cannot check, or I cannot require the curl of epsilon to vanish to ensure that epsilon is compatible with the existence of a displacement field. That's the message here. It's not good enough. I need to do something else. Okay? So that's the conclusion, and let's write that over there. Now, the solution requires a little bit analysis, and perhaps to your liking, I will skip the details. If you are interested, of course, I can always tell you about the details, but for our purposes, I want to just make it practical and eventually give you directly what the solution to this, or the remedy to this problem is. So our conclusion is that the curl of epsilon is not equal to 0, even if there exists a displacement field from which the strain comes. Okay? So to check compatibility, you should not be checking curl of epsilon equals 0. We must check something else. And here's the remedy or the solution to our problem. And here I am skipping the details. So you check. So in the upcoming weeks, I'm going to use different terminologies. Sometimes I will say check. Sometimes I will say require. Sometimes I will say enforce compatibility. So in any case, let's say to check the compatibility of the strain field with the existence of a U, we want to check not only a single curl of epsilon, but two curls. So if you take two curls and if it's equal to 0, then epsilon is compatible. And these are called eventually the compatibility conditions. The compatibility condition. Now, if you write this thing out, it's a little bit ugly. There are indices flying all over the place. So I'm going to write here, there's a sum, but actually there are 4 sum signs. One of them over I, another over J and K and L. And there are 2 permutation signs because there are 2 cross products here, right? This is eventually, in practice, what one needs to check. But I will make your life even easier now. And give you directly the final implications of that equality. Right? So in practice, what you would have to do is you have to go in here. There's a sum over IJKL. So I need to plug here 1, 1, 2, 2, and then for K, 1, 2, 3, etc. R and S, there is no sum over R and S. So for any possible choice of R and S, this has to hold. Okay? But if you do the math, right, so remember, for instance, if any one of these indices, they're repeated. So if it's like 1, 1, 3, it's 0, right? And if it's 1, 2, 3, it's 1. If it's 1, 3, 2, it's -1, etc. So there's a lot of simplification. And at the end of the day, explicitly, you get only 6 equations that are different from each other. Okay, so let me write them explicitly. There are 6 in 3D. Okay, and by default, I am always assuming that we're in 3D. So the compatibility equations are. And notice also I am assuming Cartesian coordinates. Because just like gradients, curls also look different in different coordinate systems. So eventually, when we need them, we can get them out of references. Here, the results are in Cartesian coordinate system. So there are 2 curls, which means, right, I have 2 derivatives. I see that explicitly here, right? So for every component, I have 2 derivatives. Okay, and one more to go. So these are the 6 equations that we have. Okay, so this is in 3D. Again, in Cartesian coordinates, this is how it looks. If eventually we need it in a spherical coordinate system, I will tell you the one we need in the form we need, right? But if we're in 2D, and usually our choice of indices then are 1 and 2, then pretty much you can omit everything that has to do with index 3. And all the equations except this one, each one has a 3 in it. Okay? So in other words, if you are working in 2D and your index choice is 1 and 2, then this is the only one you need. 2D for us, again, the world is 3D. What 2D means is that it's going to be eventually plane stress or plane strain problem. Okay? So that you have to just concentrate on whatever goes on in the 1-2 plane. All right. So this is pretty much it, right? So I've sort of motivated the need to check for the compatibility of a gradient with the existence of the original field. For instance, for displacement gradient, we check for the existence of a displacement field. And here also, is there a U such that epsilon comes from it? This is the condition that you need to check. If this is equal to 0, then you make sure that there is such a U. Now you can go into the effort of somehow integrating the components of epsilon towards U. And that is now what we're going to do. Okay? I'm going to solve one problem just to demonstrate the idea. Eventually, remember that when I integrate, there will always be some constants of integration or functions of integration. In this case, we got constants. For the displacement gradient, we got arbitrary constants that represent rigid body translation, because H is insensitive to that. How about strain? When I integrate, what do I expect? So for instance, is strain sensitive to displacement, constant displacement translation? From last lecture, actually, I can remind you that it's not. Okay? But not only is it not sensitive to rigid body translation, it's insensitive to rigid body motion altogether. Small rigid body motion, which means small eventually rotations are also permitted. They would not somehow go into epsilon. Epsilon is entirely insensitive to that. You would see it in H, and we've given an example last time, but you would not see it in epsilon. So eventually when I integrate to an epsilon components, towards a displacement field, I should see some rigid body translation and some possible rotation. And we'll see how we obtain these in this example. Okay, so the example is the following. So eventually, this is an example actually that we are going to solve. At this stage, I can tell you that the problem is associated with a cantilevered bar. This cantilevered bar is plane stress. And plane stress is to be interpreted as follows. So let me write down the coordinates. So this coordinate, it's x1 through the middle. Upwards, it's x2. And eventually, you can take a cross section, let's say there, and look at the cross section. And over the cross section, this is the height is 2a, the width is 2b. Okay, and this direction, upwards direction, it's x2, and rightwards direction, it's x3. Okay. So what plane stress means is that When I look from the front, this is the picture I see. So if it is very thin, then it will be plane stress. We will discuss these when the time comes. So I'm assuming that B is much less than A. I'm not going to carry on a solution of this problem. This requires that we further proceed with our approaches, and we need a few more developments that we will carry on, starting with next lecture, but also at the beginning of next week. But I'm just trying to explain the motivation for this particular example. So I have a force, and it's going to eventually bend. There will be some internal shear forces, transverse forces, and so I will get a displacement field that represents the deflection of the cantilever bar. Let me define a constant, C. This constant eventually will appear in our solution. So P is the load that we apply, E is the Young's modulus, and A and B are the dimensions of the cross-section. So actually, this is just to sort of motivate you for this strain field. So eventually it turns out that the strain field for this problem is this is nu, right? The Poisson ratio. We also don't need to know what it is at this stage. For us, it's just a constant. And then we have epsilon 1, 2. Okay. So these are the components of the strain. The last one, let me call star. Eventually, I will need this equation once again. So I know what the components of this strain are. And the question is, find U1 and U2. We are not worrying about U3 because it's a plane stress problem, and therefore I can only concentrate on whatever goes on in the 1, 2 plane. So now in practice, of course, nobody would tell you, right, in this type of a, let's say, exercise, you wouldn't know that there is an actual problem that delivers you this strain field. So when you're given the strain field and the question is find U1 and U2, now you have to be careful. First, you have to make sure that your efforts are worthwhile. So first, you check if the strain field is compatible with the existence of a displacement field. Okay? So to solve, let's begin one. Step one, check compatibility. So in other words, does there exist such a U to begin with, right? And in this case, we are a little bit lucky because these conditions are trivially satisfied, right? So this is the condition that we are trying to check. 1, 1, comma 2, 2. It doesn't depend on x2, so it's 0. 2, 2, comma 1, 1. Two derivatives with respect to 1, but there is only one x1, linear in x1, so it's automatically 0. And 1, 2 does depend on x2, but does not depend on x1. So it's 0 plus 0 minus 0. So it's trivially satisfied in this case. So now that I know that there exists such a displacement field, I carry on with the solution. And this I'd like to do because we need to do some integration. Okay. So let us raise this board. And as I do this integration, we will face a situation at some point that is going to repeat itself several times throughout the course. So there are curls flowing around, a lot of derivatives, but that's inevitable. But at least what I'm trying to do with the examples I give and with what I state on the board, I'm trying to make sure that nothing I write goes wasted. That's also true for the homework problems. So eventually, whatever you do there at one point or another will be needed or strongly complements what we talk about in the lecture. So I'm pretty much avoiding, let me say, doing things just for the sake of it or just for its pleasure, right? We are going to actually make use of the, let's say, the difficulties we face. We learn from them. Eventually, it helps us solve another problem in the future. So we're going to face one such difficulty here now. So epsilon 1,1. That is equal to, so first of all, epsilon 1,1 is del u1 over del x1, and that's equal to 2c x1 x3. Right? And so now I can go ahead and integrate this thing. So u1 is equal to c x1 squared x3. Plus function of x2. Sorry, I made a mistake. This is supposed to be x2. There is no x3, right? So we have only two indices. Oh. So actually, I apologize. So all of these threes have to be 2. We are in a plane strain setting, so 3 does not concern us. So please correct those. I was wondering where this 3 came from. OK. So now let me ask you once again. Function of x2. Okay. So let me call that function f1 because it's an arbitrary function for the first component. It is a function of x2, and let's not forget that. OK, then I proceed with epsilon 2 del u2 over del x2, and that's equal to minus 2 nu x1, x2. Right? So I have u2 equals minus 2 nu. And there's also a c minus nu c x1 x2 squared plus, in this case, a function of x1 only. And I called that f2. Now, epsilon 1, 2 is not directly a derivative of 1 with respect to 1 or 2 with respect to 2. It's rather a mixed derivative. 1 with respect to 2, 2 with respect to 1. So integrating that is a little bit tricky, right? Because here it's only derivative with respect to x1. I integrate with respect to x1. Derivative with respect to x2, I directly integrate x2. But this one has derivative with respect to both, so what do I integrate with respect to, right? So instead, what I do is I use these, I plug them in there, and see what I get. Okay? So that's equal to 1/2, right? u1, comma 2, x1 squared, cx1 squared, plus del f1 del x2. In fact, instead of del, just to highlight, I want to highlight here that f1 is a function of x2 only. Okay? As we take these derivatives, we should never forget that. For instance, if I were to write f1, comma 2, that does not quite reflect. It looks like a partial derivative, but it's actually absolute derivative. f1 only depends on x2. Okay? So then, plus u2 with respect to 1. u2 with respect to 1 minus nu c x2 squared. And then plus, again, d over dx1 in this case. F2. Okay, so of course that doesn't quite tell me anything, but now I know a little bit more. I know that actually epsilon 1, 2 has to also be equal to this, right? So by using 1 and 2 in epsilon 1, 2, I sort of avoided having to integrate this because it was problematic. There were two indices. I got an expression for epsilon 1, 2 that is consistent with this U1 and U2, but now I know that it also needs to be equal to bi star 1 plus nu c a squared minus x2 squared. So now what I'm going to do is I'm going to collect terms that are similar. In fact, I'm going to collect terms that have to do with x1 and x2 only. Okay? So for instance, right? This is a function of x2 only. This is a function of x1 only. Similarly, this here, it's a function of x1 only. And in fact, if you look at what remains, everything is at most a constant or a function of x2 only. So now what I'm going to do is first I'll write terms that have to do with x1, and then I'll write everything else. Okay? So first the x1 ones, that and that. So df2 over dx1 plus cx1 squared plus, okay, group together everything that remains. For instance, that term and that term and that term. Okay, so df1 over dx2 minus nu cx2 squared to 1 plus nu c a squared minus x2 squared. I hope you do not confuse c's with parentheses. What's special about this term? Function of x1 only. Well, let's see. This one is a function of x2 only, at most. Function of at most x1, let me put it that way. Function of x2 at most. So, what can I say? So you're saying it's 0. Why? Because it's a function of x1 and that's a function of x2. Is that why? Okay. Where? No. So what I've done is, you see, this is equal to that. So I've subtracted this from that and set it equal to 0. And that's that expression. Right? Everything's already there. So these groups of terms are supposed to tell me something. So for instance, this is a function of x1 only, right? At most. Let's say it's x1, for instance. And this is a function of x2 at most. Let's say it's x2. x1 plus x2 is equal to 0. Clearly impossible. Okay? So then, what's the trick? It should be 0. Is it okay if I say it's 0? Are you satisfied? 0 is good?
Can you explain why?
I don't know if it's 0. I just propose that it's 0. If it's 0, are you satisfied with it being 0? Obviously, 0 plus 0 is 0. It's certainly satisfying. I don't know if it's correct. So this is f2 is a function. So that's why I said I put these explicitly. f2 is a function of x1. So this is a function of x1. That's a function of x1. So this thing altogether is a function of x1. at most. Okay. This one, on the other hand, if you look, there are some constants, so it's a function of x2 at most. So a function of x1 at most plus a function of x2 at most is equal to 0 is clearly sort of a tricky statement. Okay? And because this is supposed to hold for any x1 and x2, not just for some particular choices like 0, 1, -1, 15, whatever, for any x1 and x2, which means that x1 and x2 should not appear, right, in these individual terms, because if they do, you cannot match them to 0. Okay? So that's why I said they have to be individually equal to 0. And you are satisfied with it. But you shouldn't be, because it could also be a constant. Any constant is fine, as long as there is no x1. So that's why I'm saying it's at most a function of x1. So it's not a function of x1, but it's also not 0. It is a constant. Let me call this constant theta. Okay? And therefore, this has to be equal to minus theta. Okay? Because the result is equal to 0. And this theta is a constant. So, right, hence, now, right, in all of this solution procedure so far, I did not know what F1 and F2 were. And now I know that F1 is equal, if this is equal to some constant, so now I can integrate this. So hence, F2 is equal to, right? So that's equal to a constant. I integrate towards that. So it's theta, right? This is equal to theta. So F2 is equal to theta x1 minus 1 over 3 c x1 squared plus some constant, another constant of integration, d2. Okay? I'm dealing with F2, so I wrote here d2. And similarly, now please do this at home. This is the second expression is equal to minus theta. So therefore, you can integrate F1, right? F1 in terms of x2. So F1 is equal to dF1 dx2 can be integrated. And F1 you will find is equal to, so F2 is a function of x1. F1 is a function of x2. It's going to be equal to 2, 1 plus nu c a squared minus theta x2 minus c over 3, 2 plus nu x2 cubed plus d1. So now I know what F1 and F2 are. And therefore, finally, I know that U1 and U2 are equal to, I had the expressions for U1 and U2, C x1 squared x2 minus nu C x1 x2 squared plus F1 of x2 plus 2 of x2. Huh. X1 cubed, thank you. Yes. Okay, so I integrate epsilon 1, 1, and 2, 2 towards U1, U2. Cannot integrate 1, 2, it looks tricky, so I use them in 1, 2 and get an expression that's consistent with these two. But now I know I'm given explicitly what it is. So now that's equal to that. So I collect everything on the left-hand side that set it equal to 0. And the way I collect is I collect terms that are a function of one parameter and at most a function of another parameter. And the only way these apples and oranges fit together and sum to 0 is if they are both constants with a change of the sign. So once I get this, then these two things give me two equations. That's equal to that, that's equal to that. And so I can integrate towards F2 and F1, which are unknown. So I had one constant of integration, in some sense, one constant of problem there appearing, and another one appears for each component. So overall, in this thing so far, I have two constants of integration that come from the last stage and another constant of integration, sort of a constant of the problem that comes at this stage. Okay? So these represent, as you see, rigid body translation. And theta represents rigid body rotation. Okay. And it represents rigid body rotation because you can notice here that U1, U2, there are many, many terms here, but eventually at some point, you have terms that are related to theta as follows. You have a minus theta term and a theta term. Theta multiplies x1, minus theta multiplies x2. And last time, we had written that this is the matrix in 2D that represents small rigid body rotation. Okay? So I have theta, D1, and D2. These have to be determined according to some additional conditions, some sort of eventually a boundary condition. So please carefully examine this problem. Go over it again. Go over the steps. Make sure you feel comfortable with each step because we're going to use it again and again. Okay, so if you have any grain of doubt about the procedure, just ask me. Okay, so that's all for today. Thank you.